In this lecture, we are going to go through a Colab notebook that emphasizes the importance of shapes in RNNs. Remember that whenever you hear me say something like n by t by d, you should be automatically thinking about a box without me explicitly showing you a box. If you don't have this automatic visualization reflex, you'll be at a disadvantage in trying to learn this stuff. This lecture is all about tracking the shapes in an RNN, and also we are going to go through the RNN calculation manually to reinforce our understanding of how an RNN works. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. So the first thing we have here are just some comments where I list out all the important size variables we have to pay attention to. These things should be permanently stored in your memory. You should never be asking, what does m mean again? If you are, that will significantly slow down your learning. So take notes and write things down if you have to. So just to recap, n is the number of samples in your dataset. This has been the case since the beginning of this course. T is the sequence length. Remember that in PyTorch, we assume constant size sequences. D is the input feature dimensionality. We've gone through many examples of this where you might have a d bigger than 1. M is the number of hidden units. This is the same as we have in a regular feed-forward ANN, so it's a hyperparameter which you can choose. Finally, K is the number of output nodes. As a side note, K being bigger than 1 does not automatically imply you are doing classification with a softmax. You can do multi-dimensional regression too. Imagine, for instance, you are trying to predict lat-long coordinates. In that scenario, K would be 2, but it would still be a regression problem. So next we're going to make some dummy data. We're also going to set our size variables. So we're setting n, t, d, k, and then we make x to be just a random array of size n by t by d. Okay, so n is 1. So for this example, we're only going to be working with one sample. T is 10, so our sequence length is 10. D equals 3, so our feature dimensionality is 3. M is equal to 5, so our hidden feature size is 5. Finally, K equals 2, so we have 2 output nodes. And as you know, our input x will be of shape n by t by d. Next, we're going to create our model. So as before, we're going to create a custom class called simpleRNN. This time, I'm not going to have an input argument for the number of hidden layers, since the default is 1 and so it does not need to be specified. Inside the constructor, we have the same steps as before. We set all the arguments to be instance variables, we instantiate the RNN module, and we create a dense layer with the number of output units k. And just for fun, I'll use the tanh activation as the RNN nonlinearity. Next, we have the forward function, which is essentially the same as before, but with 2 crucial differences. First, we're not going to use the GPU in this notebook, since we're not training anything. And second, instead of just taking the final hidden state and passing it through the dense layer, I'm going to take all the hidden states and pass them through the final dense layer. So now, we'll expect our output to be of size n by t by k instead of just n by k. Next, we're going to instantiate our model and then pass in x to get the model's output. So obviously, both our data and weights are random, so this prediction is not meaningful. These numbers are just for sanity checking. As you can see, the output shape is as expected, 1 by 10 by 2. This is because we have one sample, a sequence length of 10, and 2 outputs. Take note of these numbers, as this is what we want to compare with later on. Next, we're going to detach the output and save it as a NumPy array so we can use it later. Next, we're going to grab the parameters of the RNN module. As you can see, when I call the parameters function, it returns 4 things. Now you might ask, how do I know that the parameters will be returned in this order? Well, I don't. I had to figure it out by running this script and making sure the outputs were the same as my manual calculation. So as an exercise, if you want to, close this notebook and try to do it yourself. You're strongly encouraged to do so. If we inspect WXH by checking its shape and printing out its values, we can verify that it really refers to the input to hidden weight. If you recall, the input dimensionality is 3 and the hidden dimensionality is 5. Next, we just have some code to copy each of the parameters to NumPy arrays. Now, if we check the shape of all the parameters, our ordering seems to make sense. WXH we already confirmed. WHH should be 5 by 5, which it is. What's weird is that PyTorch separates the input to hidden bias and the hidden to hidden bias. That won't be a problem as long as we follow the principles. Next, we grab the parameters of our final fully connected layer, WO and BO. If we check the shape, the ordering appears to be correct. The last step is to do our manual RNN calculation. This just follows the pseudocode we discussed earlier, so hopefully you were taking notes. To start, we're going to initialize the initial hidden state to a vector of zeros. Next, we get x at index 0, which is our one and only sample. Next, we initialize an array of zeros for our y-hats. As you know, in this example, we only have one sample, so for simplicity, I'm going to make it an array of size t by k. Next, we enter a loop where little t counts up from 0 up to big T. Inside the loop, we first calculate h, that's the hidden value at the hidden layer. This calculation is a little bit different from the theory lecture, since the RNN layer has 2 bias terms. Nevertheless, we can follow the usual pattern. In order to transform x of t, we're going to multiply by WXH and add the bias term BXH. Next, we're going to take the previous hidden state, h last, multiply it by WHH, and add the bias term BHH. So that transforms h last. So they're both affine transformations on x of t and h last. Next, we add both these linear transformations together and apply the tanh activation. Once we have h, we can calculate y, which is just the usual equation, multiply by WO and add BO. And we also store the y that we get into our y-hats array. Finally, we assign h to h last so that h last has the correct value for the next iteration of the loop. Once we're outside the loop, we can print the final value of the y-hats array, and hopefully, this is equal to what we calculated before with the PyTorch model. Now, since this is just a big list of numbers, and most of us won't memorize what we saw before, it would be better to check this programmatically by using the allClose function. Awesome, so we've confirmed that these are indeed the calculations that are done by a simple RNN. One thing that made this exercise simpler was that we only had one sample. As a bonus exercise, here's what you can do. Use an n bigger than 1. Modify this code so that it still produces the same result, even when you have multiple samples.